I'll straight go to the lecture. So what I'm going to cover today is type 2 and the clinical conditions related to type 2 and type 3. Both of them are antibody mediated. Just to refresh the things that we learned, some of the things which are linked. So how many hypersensitivity types are there? Type 1 is mediated by IgE. Type 4 mediated by cell-mediated immune response. Any disease that you remember in type 1? Bronchial asthma, anaphylaxis, allergy, food allergies, drug allergies. What about the type 4? Tuberculosis, poison ivy, contact with the poison ivy. These, today the type of hypersensitivities that we will learn are also antibody mediated. They are purely IgG and IgM mediated. Now, what they will do is antibodies will either target the cell or make complexes or change the function of the cell with which they are. So the first thing is they are going to be cytotoxic. So for example, red blood cells have got receptors ABO or RH. These can bind to the red blood cells and cause damage to the cells. That's why they are called as, one group is called as cytotoxic hypersensitivity, which is type 2. The other one is, I yesterday told you that antibodies are soluble in the blood, antigens are soluble, but when they will combine, they will make immune complexes which will be deposited. Okay, so the second one is toxic complex, which is mediated by 3. So you can call it immune complex mediated disease or immune toxic complex. While the first one is causing cytotoxicity, damage to the cell, target cells, that's why it is called as cytotoxic hypersensitivity. The effector cells are phagocytes, macrophages, neutrophils, and natural killer cell, and also complement is involved in both types. The reaction time is normally 6 to 24 hours. Now we'll see what kind of damage can take place and how. So let's say IgG or IgM has bound to the surface of red blood cell, any other organ cell. It will either induce complement-mediated lysis, antibody-dependent cell-mediated cytotoxicity, ADCC. Which cell is going to cause this? Natural killer cell. And phagocytosis by which cells? Macrophages, neutrophils, monocytes. The antigen can be endogenous from the body, so it will be self-antigen, or it can be from outside, exogenous, like in the extracellular matrix, for example, drug as penicillin. Now this is the animation to explain to you what is going to happen. The IgG antibodies come, bind to the target. What is this? C1. Complement system is activated, and then MAC formation is the end result. So it will result in the lysis. So this is complement-mediated lysis. Would you like to see it again?
Yes.
Antibodies are produced against the target cells. They bind to their antigens. C1 is activated by classical complement pathway. It will lead to other pathways activation, MAC formation, and MAC will cause damage to the target cell. So very simple. Next, this is antibody and complement dependent mediated lysis. Sorry?
Is it done specific for anti-aging?
Yes.
Or anti-aging?
No, it is specific, but sometimes, as you all know, that classical pathway is more easily activated by IgM rather than IgG. So IgM are not very specific antibodies. They can be sometimes non-specific as well. But in this particular case, they are specific. So the IgMs are specific, IgG are specific. They bind to the antigen and then result in activation of pathways, classical pathways. Number 2, this is antibodies binding to the antigen, and they will act as opsonins. So these are Fc receptors on natural killer cell, and perforins and granzymes will cause damage of the cell. This is called as ADCC, antibody-dependent cell-mediated cytotoxicity. Just one more time. FC receptor binds, and then the perforins and granzyme play a role. You can just read this thing, it's just explanation of the same process. After this, interaction of antibody with the extracellular matrix. So it's not always the surface of the cell. Sometimes antigen can be outside the cell. What is the example? Best examples are lungs. So have you learned so far the structure of the alveoli? Okay, so the airway tree starting from the trachea or bronchi gradually goes, and then there are round, balloons-like structures, alveoli in the lungs. At the exchange level, gaseous exchange level, there are membranes. Similarly, in the kidney, the glomerulus, it has got a part where there is ultrafiltration and formation of the urine. So both the membranes of the alveoli or of the kidney, glomerulus, they both have got sometimes targets in certain diseases. And what happens is, so just consider this is the membrane, and these round structures are the epitopes or the antigens. Antibody will bind to it, and now the way you saw now, classical complement pathway will be activated. You can see C3b, C5b, these complement proteins are activated. They will call upon more neutrophils, and all together they are going to cause damage to this membrane. So it's not just the cell, but sometimes extracellular membrane or extracellular matrix that can be damaged as well. This is again just to emphasize or reinforce that opsonization can be done by complements and antibodies. It will result in phagocytosis, and here we are showing you that you can see complement was activated, complement protein C3b bound, and then at the same time antibody bind. FC receptor is causing opsonization and C3b is causing opsonization. As a result, macrophage has engulfed the whole target cell. Now, we will see the clinical conditions which can be because of this cytotoxic hypersensitivity. What is alloimmune? What is alloimmune? Simply among the species. So among humans, there are structures which are different from one to another. So my MHC is different from your MHC. My fingerprints are different from your fingerprints. This difference is like a foreign. So if you take one person red blood cells, give it to another one who are not the same blood group, there is going to be transfusion reaction. So this ABO is blood group A, B, and O. RH makes them positive or negative. So in both the cases, if it is not compatible, there is going to be a reaction, and this reaction is type 2 hypersensitivity. Another is altered function. We'll see that the antibodies sometimes bind to the cell and will change the function, either make it more or it will stop the function. Both the examples we'll see. One example is of thyrotoxicosis. The thyroid gland, it produces thyroid hormone. So some antibodies can bind to the thyroid gland cells and cause them to produce more hormone. That's why it is called as hyperthyroidism. While on the other hand, sometimes they can block the nerve impulse transmission in myasthenia gravis. I'll show you both the things in detail. Then another thing is autoimmune conditions have got hemolytic anemia. And yesterday I talked about the rheumatic fever, where was, not yesterday, day before yesterday, about the molecular mimicry. So the antibodies are produced against the pathogen. Pathogen is gone, but then the antibodies attack the heart valves. So these are destructive, these alter the function, and here just the allo group basically is that we all have the same antigens, but yet when there is mismatched or incompatibility, there will be reaction. Now this is the example of the mismatched transfusion. This is blood group A person, this is blood group B. If the blood group from this person is given to the B1, there is mismatched transfusion, and all the people, so blood group A has got antibodies against B, blood group B has got antibodies against A. So these are called as preformed antibodies, IgM. So when the red blood cells came, his antibodies, IgM, targeted the red blood cells, and what will happen? Complement-mediated lysis, phagocytosis. That already you saw in the animation. Now these are just certain features to tell you that what happens during the mismatched transfusion. There is, first of all, the patient looks, anxiety increases, wheezing and dyspnea, the patient is not able to breathe, the blood pressure drops, and the patient becomes febrile, his heart rate increases, his breathing rate increases, and he feels headache, and finally there is chest pain and low back pain, hemoglobinuria. So these are gradual changes that are taking place in the patient that we show. Incompatible transfusion, cells will be destroyed, and all these features will be seen. Another condition is RH incompatibility. You have heard this? Yes. So the mother is RH negative, baby is RH positive, antigen seeps from the baby into the mother, antibodies are produced, then those antibodies come back and attack the baby in the next pregnancy, not the first one. And this is how the patient looks like. Now here's the question, why do antibodies to the ABO blood group that are normally present in the mother not damage the erythrocytes that are present in the fetus? She is carrying when the fetus has a different blood group. I'll try to make it easier. Sorry? First exposure. Okay, there is a mother, she is blood group A. Here is the baby, blood group B. And same baby has got RH positive and RH negative. In the RH case, little exposure is going to cause antibody formation and those antibodies will go and cause damage. But ABO is also incompatible.
IgM doesn't work.
Then why IgGs are not produced?
Because it's not produced, IgG.
Why?
Only in exposure, there is formation of IgG and
Do you all agree with this? He says IgM does not cross the blood-brain barrier. But why IgGs are not produced? Excellent answer. The actual problem is not with immune deficiency, first exposure, second exposure. So the red blood cells, here is the RH antigen. This is an RBC. And same RBC has got ABO antigens. ABO antigens are carbohydrates. While RH antigens are protein. In both the cases, when the exposure will occur, carbohydrate antigens have got against them just IgM formation. They will not be presented to T cell, there will not be any class switching, so no IgGs are formed because no class switching, no T cell help, no T cell help. Here, there is class switching and T cell help because it's protein in nature. So there will be class switching here and IgGs are formed. And then IgG can cross the placental barrier while IgM cannot cross the placental barrier. So the difference is always there. If there is difference of blood group A and B, but because here is no class switching, no IgG form, IgM cannot cross. So that's why you don't have this problem of RH incompatibility. You don't have ABO incompatibility. That occurs only in transfusion reaction. But in babies, you have just RH incompatibility because of the protein antigens. Okay? Everyone is clear now? So this question basically is this. So you should know that which ones are carbohydrate antigen, which ones are protein antigen, and what it will do. Now the next thing is autoimmune hemolytic anemias. So the autoimmune conditions, why they result in hemolysis and what will happen with that. So warm antibodies are IgG class, cold antibodies are IgM class. One is going to cause intravascular hemolysis, the other one is going to cause extravascular hemolysis. We have already discussed this, but you remember all this? Intravascular hemolysis is caused by IgM, because IgM again cannot go out of the blood vessel. And IgM is going to activate the classical pathway. Now you saw that the complement are going to damage the blood cell inside the blood vessel. While IgG they are not very effective at activating the complement system. They will just bind and do opsonization, and then that will take place inside the spleen. So extravascular IgG mediated, intravascular IgM mediated. So this is IgG bind, the cell going to the spleen, so extravascular hemolysis. Do you think rheumatic fever is a type 2 hypersensitivity? Yes. We now said that the tissues, if targeted by the antibodies and then the complement activated or natural killer cell activated, they are going to cause the damage. So yes, how it happens? So rheumatic fever basically is hemolytic streptococcal infection. About 10 to 14 days later, the joints of the patient gets inflamed, heart valves are involved, skin has got rashes, sometimes the nervous system involved as well. And what is the system of that? Basically, you can see that now I slightly am not 100% in favor of what is here shown. I think it's not just the antigen deposited here, is in fact antigen and antibody sometimes complexes also are formed that can be deposited. So both ways. And then the complement activation or natural killer cell activation, and finally there is tissue damage. And main reason is molecular mimicry. Now we'll talk about the altered functions, how these IgG or IgM can alter the function. So here is a case of hyperthyroidism, which is also called as whiter. The thyroid gland has got special cells. These are the thyroid cells. They have got a receptor which is called as TSH, thyroid stimulating hormone receptor. So actually they are waiting from the signal from the pituitary that comes to the thyroid to prepare thyroid hormone or to stop. So this basic receptor is for the stimulation. And there are autoantibodies formed against this receptor which will behave like the signal from pituitary, but they are actually nothing. And once they stimulate it, thyroid gland keep on producing the hormone. That's why hyperthyroidism or thyrotoxicosis, and it will result in the enlargement of the gland. And this condition where the eyes propped out is called as exophthalmos. Yeah? So from the brain, in the pituitary gland, there is a hormone released which will act normally on thyroid cells, which have got receptor for it. So this hormone is going to activate the thyroid cells to produce T3, thyroid hormone, and T4, trioxythyronine and tetraoxythyronine. Now, in this condition, autoimmune condition, it's not the hormone, it's the antibody. So autoantibodies are produced against this receptor and acting like this, so stimulating it. So more and more T3, T4 is produced, hormone levels are increased in the body. That's why it is called as hyperthyroidism. Okay. Now the other condition is normally at the synapses there is the nerve muscle end plate. The acetylcholine is contained in the membranes. Okay, so whenever the nerve impulse transmission occurs, these acetylcholine are released into the synapse and then they bind to their receptors. So these acetylcholine receptors are activated and nerve impulse transmission carry on. In myasthenia gravis, antibodies will be produced against these receptors, so they will block them. And when the actual acetylcholine is released, it will not find the space to bind with these receptors. So when the nerve comes, there is no transmission further or no signal to the muscle. And gradually as the day passes by, so at the start of the day, the patient is okay, but gradually you can see his eyes starts to drop. Muscle weakness, because there is no acetylcholine to give the signal for the muscles to work properly. And gradually the patient's muscles weaken. That's the disease. Myasthenia gravis. Myasthenia is for muscle. Asthenia is weakness, muscular weakness. And gravis is severe muscular weakness. Why? Because of the receptor blocking. So we saw two conditions. In one, the function was increased, and in the other, the function was blocked. The one where the function was increased is called as hyperthyroidism. Why? Because the antibodies are acting like hormones to activate which receptor? CSH. And in myasthenia gravis,
There is no
yeah, the acetylcholine receptors will be blocked, so the signal from the nerves to the muscle is blocked, and gradual weakness of the muscle takes place. Now, can you detect these conditions? So we have just put here two examples to find out if the patient has got autoantibodies or IgG or IgM against the target cells. You can do direct Coombs test or indirect Coombs test, and then we'll focus mainly on the RH incompatibility and ABO incompatibility. In the first case, the direct incompatibility is what? When the RBCs, red blood cells, already have got antibodies against them. So in case of RH incompatibility, if you take out the blood sample from the baby and it has got antibodies from the mother that have crossed the placenta and now bound to the red blood cells, you just put the Coombs reagent and it binds here and make a clump. Agglutination means clumping. When the clumping occurs, you say the test is positive. So what you did, just one step, took out the blood cells from the patient, put the Coombs reagent, clumping seen, test is positive. It is called as direct Coombs test. And what does it show? It shows that the antibodies were coating the red blood cells. Okay, this is direct Coombs test. On the contrary, indirect Coombs test, what does it have? It has got the red blood cells and the antigen, but the antibodies are in the serum, not on the surface of the red blood cells. So you will first take the red blood cells and the patient sample, put it onto the red blood cells. They will first coat the red blood cells. After that, you will take the reagent and put it, and that will result again in clumping. So it's indirectly. First you find the antibodies, put them onto the red blood cells, they coat the red blood cells. Then second phase, you take the reagent, put it there, and they result in clumping altogether. Is that okay?
Indirect.
Yes, in the indirect. This is what's happening.
No, I didn't understand.
Okay. In the first phase, the red blood cells are already coated with the antibodies. Okay. How many steps you are doing? You are taking the patient sample, you are taking the Coombs reagent, putting it together, and you get the reaction. What is happening in the second one? The patient sample has got antibodies. It does not have the red blood cells. The red blood cells are separate. Okay? You first mix the red blood cells with the patient sample so you can get this kind of situation. You see now at this place, red blood cells are coating the red blood cells are coated with the antibody. After that, you add this kind of Coombs reagent and then clumping set. So it's a two-stage process. Stage 1, add the serum sample. Stage 2, add the Coombs reagent. Here you directly add and you get clumping. Okay, this is test red blood cells. These are not from the patient. So the kit has got red blood cells. You just take the patient serum. So what it tells you, the end result is what the Coombs test is telling you. If there are specific antibodies produced in that patient which are coating the red blood cells, so they are directly targeting it. But in this case, there are antibodies which have not yet targeted the red blood cell.
You try to do the first way, there is no result.
Then you do the indirect. Yes, it's always like this. You do the direct and then you do the indirect. And this will give you information regarding the type 2 hypersensitivity. Now so far we finished. You want me to just quickly recap?
Yes.
Number 1, type 2 hypersensitivity is caused by IgG and IgM. They will either be produced against the target cells which have got the antigen, or they will bind to the body cells and alter the function. Okay? When either they bind directly or indirectly to the extracellular matrix, they are going to activate the complement system, but mainly through IgM, or they are going to cause opsonization mainly through IgG. Okay? When complement mediated action takes place, there will be induced death or damage to the target cell. On the other hand, there is opsonization and phagocytosis by macrophages and monocytes or neutrophils. They can also do one more thing, natural killer cell mediated damage. So they opsonize the cell and the natural killer cell comes, so ADCC, antibody dependent cell mediated cytotoxicity. This is the damaging mechanism, complement, natural killer cell or phagocytosis. Now what are the conditions that we roughly talked about? ABO incompatibility, RH incompatibility, or autoimmune conditions where antibodies are formed against the target cell. One important thing that I taught you here is that the RH and ABO, both of them does not have all the time problem, and the main reason is that in one IgM is formed because of the carbohydrate antigen, in the other IgG is formed because of the protein antigen. This will lead to RH incompatibility, but this does not lead to ABO incompatibility. Then finally, the two conditions where the altered function is seen, antibodies are produced against the TSH receptors of the thyroid, increase their hormone secretion, hyperthyroidism. On the other hand, myasthenia gravis, the antibodies block the acetylcholine receptor, nerve impulse transmission from the nerves to the muscle is blocked. As a result, there is muscle weakness. Is it okay so far?
Yes.
Okay, the type 3 hypersensitivity is because of the immune complexes or toxic complexes. Now, the important thing here is that which is the site of immune complex deposition, not the formation. So once the immune complexes are formed in the blood, you have to remember this thing, that immune complexes, formation of immune complexes is normal or abnormal? Normal. Who clears the immune complexes from the blood? Spleen. Macrophages, very good. So the immune complexes will be cleared from, so first thing is complement is going to disrupt the big complexes. Okay? Big complexes formed. They will be disrupted by the complement proteins. Which complement proteins? C3b, C4b. Their job is first to make these immune complexes small. After that, the macrophages are going to eat up small portions of it and take it to the spleen. That is the normal process. But what if the immune complex formation is increased? Too many immune complexes are formed, then the body cannot clear it up. The complement will not be enough to clear it up. Macrophages will be tired. These immune complexes then will be deposited. So that's why the important point is the site of immune complex deposition, where they are deposited, and not by the source of antigen. Antigen may be microbial, self-antigen or environmental antigen, but where they get deposited, if they deposited in the small arteries, they lead to vasculitis. If they deposit in the kidney, they result in nephritis. In the joints, they result in arthritis. And mostly it occurs in the kidney and the joint. Why? Because the synovial fluid that is formed in the joints, it is by high pressure. Okay? When there is high pressure, these immune complexes are deposited. Same is with the kidneys. For the glomerular filtration and formation of urine, there is high pressure in the Bowman's capsule. So that's why they are deposited on the basement membrane of the Bowman's capsule. And that's why more nephritis and arthritis. Why vasculitis? Because blood vessels are the first structure, especially from big vessels. When they go to the small, the pressure is too much. So they can still cause the damage and get deposited in the blood vessels. Now this is what is happening in the blood vessel. Immune complexes are formed. They will activate also complement C1 classical pathway, and MAC formation will occur. They will also recruit more neutrophils, more phagocytes, and they will release their proteases. As a result, you can see the wall of the blood vessel has been damaged or inflamed. This is called as vasculitis. Again, immune complexes activate classical pathway. As a result, there is MAC formation, more neutrophils or phagocytes recruited. They release their enzymes, and as a whole, the wall of the blood vessel is damaged.